Thanks, everyone. I think we're going to reconvene. And so this is a topic that our two speakers have been discussing back and forth, as you saw reflected in their talks. So it's really exciting to have a chance to have a more open-ended discussion, as well as the talks we heard. So I'll be keeping a queue of questions, or calling on people as the need arises. But we'll maybe get things rolling with a question of my own. So I think one issue that was crucial in both of your talks was the question of how to distinguish between what should be fundamental in physics, or what should be features of the laws, or fundamental geometry, versus what can be derived, or what should be treated as less fundamental. And I think one way of coming at that is thinking of the kinds of resources that open up, given different answers to that question. So if you treat something as fundamental or as a feature of the laws, you're committed to a certain account of it, whereas if you treat something as not, and so in general, we see all sorts of ways in which the phenomenological features of the world are not directly reflected in the laws. So one possibility then is that you can give different kinds of explanations of those features if you treat them as perhaps due to initial conditions of particular types of systems versus laws. So I think this was a theme that was present in both your talks, and I think you seem to take very different lines on this, where Tim, you thought that there's a way of putting time direction is a fundamental feature in the physical geometry, and that was something that you think is incredibly appealing and motivates this reformation of the standard ways of thinking about geometry, whereas I think, David, you were pushing more towards thinking of certain features as derived.
Maybe there's just one initial point of clarification about that. There's a way of looking at what Tim has done as a piece of mathematics, which I think is neutral between these two.
Right,
and I think it's a beautiful piece of mathematics and really intriguing, really interesting. It seems to me, I agree with a lot of the claims about this making notions of openness more intuitive and so on and so forth. So there's a huge swath of that, which it seems to me is neutral, between these views. The question is whether I'm just jumping. Should I just jump right in?
You go.
So there's here's a way to start a discussion. If there is this fundamental directedness that Tim is thinking about, the dynamical laws don't latch onto it. Okay, that is, the dynamical laws of classical mechanics, the Schrodinger equation, so on and so forth, are time reversal symmetric. Okay, they could be formulated in either, that is, they allow processes in both directions in exactly the same way. Given that that's the case, if you want to give an account of, say, if you want to give a satisfying account of how I know there's a chair in the room, the existence of the chair plays a dynamical role in my coming to say, a full explanation would involve, neuroscience, which we don't have at our disposal yet, and so on and so forth. But presumably, the existence of the chair would play a causal role in my coming to say, there's a chair in the room. Whereas, on a view like Tim's, one of the puzzles is that we make these judgments. This is before this, as Tim did in his talk. Okay?
It was.
Right. These judgments we make are physical acts that we do, are physical events. We write down the judgments. We make utterances that express the judgments, so on and so forth. Those are coming to make the utterances that we do, are coming to write down the inscriptions that we write down, are going to require an explanation, presumably, in terms of the laws of motion, okay? So that the direction of time being what it is on a view like Tim's isn't going to play the role in our judging that this was before this, that, say, there being a chair in the room is going to play in our judging that there's a chair in the room. So the worry is that the worry is that positing a fundamental direction in the way Tim wants to do leaves it disconnected in a way that ought to be worrying, it seems to me, from From the way this information from questions of the way this information gets to us.
Right. So let me just add a question to that, which it wasn't clear to me whether the new foundations of physical geometry would also lead to a new theory of dynamics. So one way of answering David's last point is just to say that actually, if you formulate the physical geometry for space-time, you shouldn't have Einstein's field equations. You shouldn't have a Hamiltonian this time reversal invariant. It wasn't clear from what you said whether that was a place you were going.
So look, there are many points. Let me try and take. Let me just point out some things linguistically, which I think are important and can mask what I take to be the kind of gap between us. So even Chris, when you began, you said, look, there are some things that are explained by the laws, and some things don't follow from the laws, but you also need initial conditions. Right? That was you said that.
Yeah. We've
got it on tape. Right. Initial conditions. The initial and initial conditions is important. Right? It was sort of thought to be a great triumph in the scientific revolution that we gave up what were called teleological explanations, which were explanations that appealed to the future, in favor of mechanical explanations. This is another thing where just historically what mechanical meant.
Right.
No. Explanation always runs from the past to the future. Okay? Now, if you don't think there's a fundamental distinction, physical distinction, between the direction from past to future and the direction from future to past, it's a little bit mysterious. I mean, this is what Hugh Price gets himself into, because he really believes that. He thinks there's no distinction. So all of that talk of initial conditions can't mean what one initially, or it's going to be problematized. The talk of causation gets problematized if you think causes have to precede their effect. The talk of how do we get the information. Think of the word, how do we acquire information? It's time directed. It means at an earlier time we don't have the information, and at a later time we do have the information. The other thing is called forgetting. So the time directedness of all our vocabulary, and therefore all of our explanations that use normal vocabulary, right? It's very hard to imagine extracting it and seeing what would be left of what we thought of as an explanation at all. Now, does this show up in the physics? Well, there are a couple simple points. When David says the laws of physics are time reversible, he means something by it, but he doesn't mean by that time reversible. They're not, right? We know they're not because CP violation.
Sure.
Okay. So if you ask me, if I look at the physics, does it suggest there's a direction of time? The answer is sure it does.
No. But we doubt that has to do with the way we make judgments about the time order of
again,
this and this.
All right, but it's the physics. I mean, of course, that makes the physics from your point of view more mysterious, because you're saying, gee, when I look really deep into these equations, even for kaons or whatever, right? These kind of, gee, there does seem to be a directionality in there. Now, a lot of this. And again, this is a little technical, but if you start with classical physics, if you start with Newtonian mechanics, it's a second-order theory in time. You take second derivatives, right? Take it. Your fundamental dynamics in terms of accelerations, and the second derivatives, of course, are invariant under time reversal, but first derivatives aren't. If you do quantum mechanics, Schrödinger's equation is first order in time, and to implement time reversal, you have to take the complex conjugate. Okay, it's not so simple, and you could say that's just a reflection that there is a directionality here. Now, David's point, which is correct, right? One of the points he's worried about statistical explanation, that we all agree is that physics as we now have it, if it allows the glass to fall off the shelf and splatter on the ground, it allows for a situation we would call the water collecting itself in the glass and jumping back on the desk, right? I mean, and we want an understanding about why we see one all the time and why we don't see the other all the time. But notice the way I just described that is a temporally asymmetric description, right? Because falling down is different from jumping up. They differ with respect to what? With respect to the direction of time, right? So I don't really see, if you did things my way, I'm now going to come to the question you were asking. It is true. If you did things my way, there would be a task, so employment for academics or somebody, to see how to rewrite all of the dynamics that's been done in terms of standard topological structure in these terms, which would be an extremely non-trivial task. Okay? There are some reasons to think it would be an interesting thing to do. I will just wave my hand at this, which is that this structure allows you to deal with discrete spaces, spaces that aren't continuous, spaces where the lines end up having only finitely many points, with all the same analytical structure. So if you think, and a lot of people do think, for good or bad reasons, that space-time really is discrete at Planck scale and not a continuum, I've got a gadget that you can work with and carry over. If you rewrite the continuum stuff in these terms, you can carry that over directly and deal with the discrete case, and you get automatic cutoffs and stuff like that, right? So you'll deal with ultraviolet things and blah, blah, blah. So there is, it would be an interesting thing, I mean, I think it opens up a range of possibilities that would require a tremendous amount of investigation, which I'm not going to be even capable of, intellectually, much less in any other way. But yeah, ultimately, I would think if I'm right, the laws of physics ought to take a particularly appealing and nice form when expressed in this particular mathematical language, because if I'm right, this mathematical language is more directly representing the fundamental physical structure.
And do you expect them in particular to not have the sort of time reversal invariance properties that?
Well, as I said, I don't think, I mean,
same set of topologies.
But which time reversal do you mean? If you mean the jumpy up stuff, yeah, I think things can probably still jump up. But if you're asking, if I just look at the laws of physics, do they look time reversal invariant? I think the answer is no. I think they already don't. Once you go to a first order theory, right? I have to do stuff to implement time reversal. It's not.
Oh, I didn't realize it. So you don't think that quantum mechanics is time reversal, standard non-relativity?
Well, this is funny because we used to argue on opposite sides of this. But I mean, couple of things. Right. Because what Tim said was very rich. First of all, I don't know what Hugh is up to, but I mean, if somebody is denying altogether, not you,
yeah,
Hugh Price,
right. Sorry.
It can't be that he's denying altogether that there is a time asymmetry. He's denying that it's fundamental. That's what the discussion is about. I take it. I mean, whatever Hugh Price says, leave that to him.
Okay.
It certainly wouldn't be something I would be tempted to say. There's a dispute about, the only dispute here is not whether there's a distinction, okay, but whether it's built into the fundamental structure of space-time or not. So, of course, the resources that you rightly pointed to as being presupposed by our ordinary English locutions had better be locatable in the world, okay? And of course they are, and there's nothing about a denial that they're fundamental that carries with it a denial that these things can be located in the world. And of course it's the position of somebody who denies that they're fundamental that they can nonetheless be located in the world, just like tables and chairs and universities can be located in the world. So so I'm not sure how it helps to say, gee, our ordinary language is just suffused with time-directed terms. Yes, of course it is. Those had better be referring to some feature of the way the world is. There's nothing in their profusion in our language that indicates that the thing they have to be pointing to is something fundamental as opposed to something derived.
Let me just make a quick point here. Look, the notion of a university is not suffused in our language in anything like the same way, right? If it were, if I found that for almost every verb I used, I had to appeal to universities to make sense of it, right? I'd really worry about whether I could think of universities as derivative, right? Because the question is, what resources am I using to get from the fundamental to the derivative? So it's just, that's a misleading example. Right?
There's something there's something much more ubiquitous about time directedness than there is about universities.
And I think it plays a fundamental role in certain kinds of explanations. And as I say, in what are classically considered mechanical explanations under like we are, and that leads to a different dynamic there. Right.
That's absolutely right. Also, just a thing about, because this is maybe interesting and maybe something I haven't heard before from Tim, although maybe I'm just misreading him. Vis-a-vis the question of, say, whether one ought to think of the Schrodinger equation as time reversal symmetric. Right, we've sort of, I guess, danced around in circles, because I remember us being on opposite sides of exactly this argument once. What everybody agrees about, so there's some dispute in the literature, which I think at the end of the day is mostly semantical, about exactly what one should mean by time reversal symmetric. But what everybody agrees is true about the Schrodinger equation is, for example, that for every probability distribution of particle locations, in the non-relativistic case, there is the exact time reversed probability distribution of particle locations that's associated with another solution to those equations of motion. So as Tim said, in terms of talk about whether the water can jump up from the ground and put itself back in the glass, all of the theories that we take seriously, quantum mechanics, classical mechanics, so on and so forth, whether they're fundamentally formulated in terms of a first derivative or a second derivative, agree on that, okay? Second of all, it's not the sense in which the Schrodinger equation, something like the Schrodinger equation, fails to be time reversal symmetric. I don't see any reason why that has to be taken as gesturing towards a fundamental directedness of time. All you need by that, all you need mean by that in order to be coherent is take a very explicitly and manifestly time reversal asymmetric theory like the GRW theory of collapses. All you need mean by that is that all the collapse events line up in a certain way, but it doesn't imply a distinction between this set of events and the same set of events flipped over. So there are two things to say about this. Thing one is the sense in which, say, something like the Schrodinger equation might fail to be time reversal symmetric on a certain construal of what time reversal symmetry means, a construal that I once argued for. That's not going to affect these judgments about whether the water can jump back into the glass and so on and so forth. Second of all, even if it's granted that it fails to have that mathematical property, I don't see any reason to think of that mathematical property as gesturing towards some feature of the structure of what we're calling the background arena itself. But let me ask Tim. So Tim, you seem to take up Chris's suggestion. Well, I don't know if you did or not. Chris seemed to be asking, do you think this view of the structure of space and time, the one that you have, is going to force changes in, do you think that, he seemed to be asking, do you think the existing structure of physical laws, say the Schrodinger equation or the Dirac equation or something like that, is going to turn out to be incompatible with your idea about the structure of space-time? That it's going to force, and it seemed like you said yes or maybe or something.
Incompatible, look, you're using some mathematical resources to write down these equations.
Right.
And in all the standard cases, you're using a background manifold, differentiable manifold, blah,
right.
blah, blah. Okay. So if you're going to say, all right, I'm going to switch to a different mathematical language that doesn't have those resources,
sure.
Of course, I'm going to have to sort of rewrite things. Now,
yes.
when the rewriting is done,
right.
it leads to what looks like a substantial difference that might
right.
show up in terms
right.
of predictions,
right.
Empirical predictions or not.
Right.
I don't know.
Okay, fair enough.
Right?
Good.
But the
Good.
work, would have to be done. You'd have to
Good.
sort of trace it out and see how it goes.
Good.
Right.
Good.
Okay, we have a question from the floor, Phil.
Very interesting talk. So I must say my mind's been stretched. I have a question about the line theory, or the line primitive.
Yeah.
It seems to me that comes with a bit of baggage. You've got the well-ordered or an ordering principle already built into it. Is it hiding other scary things like the axiom of choice and things like that?
Nope.
That was.
The entire theory. Look, the entire theory. In fact, the Archimedean axiom you would have to add in addition to it. Right? I can give you linear structures because the fundamental geometrical thing that's doing all the work is just a linear order. I could have infinitesimals. I could violate the axiom of Archimedes when I put metrics on this stuff. It's very, very, very weak. So, I mean, your thought that, gee, is there something scary? The answer is no. And actually, it gives rise to a tremendous variety of what you'd think of as exotic geometries.
This is an ordering principle that isn't
That's right. It just, standard topology just, again, the notion of a line is highly derivative in standard topology. And the interesting thing about it, let me just make a comment there. When I had that picture and I had a line up here, you'll notice that in the definitions in standard geometry, the way you even get to a curve is by a continuous map from the real line into the space. That definition privileges the structure of the real line, right? So suppose I thought they were infinitesimal. Suppose I had a richer linearly ordered structure than even the reals, right? Suppose I did non-standard analysis. That's the standard definitions. They're the ones who, as it were, surreptitiously restrict themselves definitionally to things that are actually generated out of the structure of the set of real numbers. Mine's much more open than that, actually. So what happens in my case is I then have to say, all right, let's restrict ourselves to Archimedean linear structures, right? Once I've got a metric, I can define what it is for it to be Archimedean and so on. But in terms of the basic definitions, they actually have very exotic instances, which are, give rise to interesting structures.
It all came a little fast.
Sorry.
Other questions from the floor? So I had a question for you, David. This is, I'm trying to remember exactly how you formulated the sort of arena proposal, but there was a worry I had that arises in a different context in programs of quantum gravity, where people try to get rid of as much background structure as possible.
Right.
And you end up with this question of, in effect, you're trying to write down dynamical equations on thin air.
Right.
You really are trying to get
that's a really good question.
background structure. So for your case,
I mean, thin air is even a lot compared to what you're writing down, to what you're writing them down on. So if you go back to the classical case, and actually I mentioned at the time, this little caveat that I put in, that of course classical particles aren't going to be enough to build tables and chairs out of, and so on and so forth. That's even more important than might have been apparent while I was reading it. It seems to me that if you were to stick to the classical case for the moment, you say, look, I have a case of a Hamiltonian on a background Euclidean space. It gives rise to flat three-dimensional Euclidean appearances in scare quotes. And then you have a claim that if the first thing is true, then it seems unavoidable that this other Hamiltonian on a background curved space is also going to produce flat Euclidean appearances. Good. What does that suggest? What's the necessary condition for producing flat Euclidean appearances? I take it the necessary condition must be something like the distribution of matter on the background space is such that a coordinatization of the manifold exists, where it's governed by a Hamiltonian that takes this form, Now you ask, gee, what kind of features of these trajectories is it going to be, in virtue of which it's the case that some coordinatization exists on which the Hamiltonian would look like this? The only available structure you have left is the topological structure of these trajectories, the extent to which they're knotted or intersect or something like that. And it looks on the face of it as if that's likely to be much, much too sparse a structure. That is, there are going to be too many ways of choosing coordinates where you can get it to obey any equation you want, Certainly, for example, if the world consists of one such particle, one such path through the manifold, and if the path doesn't happen to intersect itself or to knot itself, which such paths can do, then it's clear you can get it to obey any equation you want, by an appropriate change of coordinates. So that's going to be really bad, Right. So you need a much richer topological structure than that in order to get any constraints on what equations this is obeying. You probably need something like a field structure, okay? With a field structure, you have something going on at every point, okay? You have much, much richer set of topological relations, and it begins to be, I actually went and spoke to some topologists about this, and they said, look, you shouldn't get pessimistic so quickly because you have no idea how many topologically different varieties of knots there are in three-dimensional space, and actually it's not obvious that there isn't enough structure there to do that, but it's also not far from clear that it is, and this is apparently a question about topology that nobody even remotely knows the answer to. But there might be an interesting argument implicit in all this that the whole structure wouldn't make sense without some kind of plenum, okay? Without a field structure or something like that, where you get a much richer set of topological relations. But anyway, this question about it being written on air is very relevant. I take it on a view like the one I was pursuing here. Now, you might want to pursue this even further and derive topological structures. I have no idea how to do that. That is, physically. Tim has an idea of how to do it mathematically. But if you were just to come to rest at a differentiable manifold like I was doing, yeah, all that seems to be available is the topological structure of the stuff that's distributed over it. And there's a real, highly non-trivial, very interesting mathematical question about what would suffice to uniquely pick out such and such a Hamiltonian or such and such a set of appearances. It might be that this is a reason that we haven't stumbled over before, why the world, why things like, why worlds like ours wouldn't make sense without there being fields. I don't know, but that's a really good question.
Can I actually just make a comment? Because I think this is also a place where we come at things from slightly different directions. What David wrote down always was in terms of coordinates, right? He wrote down his Hamiltonian, and then it arose that the condition was, well,
an interrogation.
If there exists a coordinate
right.
system in which,
right?
And if you think about, your curved space that gives rise, in the way you were saying, to Euclidean appearances,
right.
Of course, what would be weird about it is that the Hamiltonian would be very strangely variant. I mean, thought of in terms of the background curve geometry, it would be just fluctuating around in kind of inexplicable ways, right?
I mean, it depends how the background geometry is curved.
Right,
but
you were doing it for an arbitrary.
Case,
you were doing it for an arbitrary case.
Absolutely right.
I mean, look, my own approach to this, and this is actually part of where I ended up doing this thing, is I don't like to think in terms of coordinates at all, because I think coordinates aren't physically real, right? I would like to put into my Hamiltonian, as it were, physical quantities, not coordinates. And if I use coordinates, like say if I'm doing special relativity and I use Lorentz coordinates, I use those coordinates, I justify the picking of those coordinates by the symmetries in the space, but I think the geometry of the space is what's fundamental. And it's in terms of the geometry of the space that I then argue that these are nice coordinates, right? And maybe I'm not surprised that the Hamiltonian takes a pretty form in terms of these coordinates, because these coordinates already adapted to the fundamental geometry of the space. Now, the way David thinks about things, he's sort of thinking of the coordinates first, and so that, if you think the geometry is arising from appearances and you understand the appearances in terms of the existence of coordinates, we're back again to what gets explained in terms of what.
Hang on a second.
I think one issue is what would the coordinates be adapted to, right? If you've already
there's
right. So
there's a way. There's a way in which I agree with Tim's characterization, I guess up till the last line. That is, it's definitely the case that that there's a sense in which Tim is starting with the background geometry, and I'm starting with the dynamics. I'm starting with the Hamiltonian. To say I'm starting with coordinates doesn't seem fair. Like we were just saying, that what Chris's question quickly led to is, the real dynamical laws are gonna take the form of some claims about the topology of the distribution of matter and fields or something like that. It's going to be then deducible that given that topology, that one of the features of such and such a topology is a guarantee that there exists a coordinate system that has such and such properties. But it doesn't seem fair to say I'm starting out with coordinates. It does seem fair, and I think it is a deep difference between our approaches, that your spade gets turned, as it were, at the level of geometry, and mine does at the level of dynamics. That's right. But have we suppose that, I don't want to hijack that. Well, just quick. So suppose, I wanted to press you once more on this question that we started with. Suppose, I guess things might come out several ways. But suppose that in your words, once we rewrite physics in your mathematical language, we don't come out with what you were calling a substantively different physics. Then is there a worry, or am I misunderstanding something of the form, gee, if that's the way it comes out, if we've still got these time reversal symmetric equations in the sense that we were discussing and so on and so forth, and somebody says, gee, on that kind of a view then, our impression of time being directed doesn't have anything to do with the fact of times being directed. That the fact of times being directed on this kind of a view doesn't play any role in explaining our impression that time's directed, because the thought is the only thing that could explain impressions like that is something dynamical. And if it comes out without these substantive changes, there won't be any sense in which the dynamics is latching on to this direction.
Yeah, I guess I don't agree. I mean, look, there's the sense of lack of time direction, and we're just going back, that you were worried about in time and chance, that we agree about if there are Foliage cups, there are jumpy cups. And my point was, yeah, and on the face of it, a Foliage cup is just physically different than a jumpy cup, and the difference is what's happening earlier and what's happening later, right? I mean, in the Foliage cup, the earlier state is up here and the later state is down here. And now, the fact that a physics that allows the one, in terms of its laws, that there are solutions, models of it that allows the one, always allows the other one. Okay, that's an interesting observation. I don't see that observation goes any distance to suggesting that the directionality isn't there. In fact, the way I normally describe it is in these directional terms. Look, Foliage cups are different than jumpy cups. The question of why do we have the impression, how do I know, did the right hand go first or the second? I mean, I take it the story about that is going to be, again, a kind of causal story about sound waves coming from this snap into my ear, affecting my neural state, a later one coming, affecting my neural state, getting a final neural state, doing computations over that, blah, blah, blah. To me, that's all time directed. Everything I just said was time directed, right? If I reverse that, it's uncomputing and throwing stuff out of my ears and so on.
Let's just register the fact that maybe this won't be something that you find bothersome or anything like that.
Yeah.
The role it plays, so it seems fair to say that the role it's playing in the causal explanation, the role the directedness of time is playing in the causal explanation is, as it were, as a condition of the possibility of causal explanation.
Yeah. Right.
Simplicity.
That's why I'm so puzzled about trying to get rid of it. Yes.
It's very unlike the role that, say, the existence of the lectern is playing in the explanation of my impression that there's a lectern in the room.
So that I don't understand. So
okay.
So the lectern, as a physical object, has a geometrical structure in space.
Yeah.
Right? And that geometrical structure plays a role in explaining why the light bounces off of it, and
right.
the structure of the optical array that goes into your eye,
right.
and blah, blah, blah.
Right.
That pair of events had a structure in time. Right? It has a geometrical structure in time.
But wait.
Okay.
A minute ago, it sounded like you were saying, and you were nodding your head when I said this, that the role that the directedness of time is playing in these explanations, that the fundamental directedness of time is playing, is just in making causal explanations possible in the first place. You were appealing to the fact that if you don't say what happened earlier and what happened later, I don't understand it to be a causal explanation.
Right. So it was the just, maybe if I said just, I misspoke.
Okay.
I do believe it plays that fundamental role, which is why trying to eliminate it or recover it puzzles me. but I'm not committed to the just. I mean, I just gave you an example. So you would say, okay, I think those events had a geometrical structure in space-time just the way the lectern you think has, and that geometrical structure plays a role in explaining what how you perceived it and why you came to the judgment of which was earlier and later. Sure. Okay. I mean, there's that part as well, right? So it doesn't disappear entirely into the background. Yeah.
Okay, further questions from the floor? Yes.
I had a question for Professor Maudlin. In terms of talking about things that are primitive and derivative, you gave the example of like a center of mass is not something that we'll find if we go and investigate a physical body. In what sense, if you want to say that time is fundamental, could we like find it if we want to look for it?
It's such a funny question because I don't know how you ever manage to lose it. I mean, you're sort of aware all the time of things happening in a certain order, right? I mean, you could tell me who went first and who went later in giving their presentations, and I'm not, the idea, the problem about the center of mass was that it actually is a well-defined location, but there's nothing physical in that location, right? The world is presented to us. So there's a piece of methodology here that maybe I should explain. The world is presented to us as having certain kinds of structure, right? Before we do science, it has to be, because it's on the basis of those presentations that we have something to do science about, right? We have some input to our science. If it wasn't, if the world was a blank to us initially before I had physics, I would never develop physics. It's presented to us offhand as having 3 spatial dimensions, right, and no more, for example. Now, that might turn out to be wrong. All right, so if string theory's right, maybe there are these little tiny dimensions, blah, blah, blah. If David's right, it's a whole different story, much more complicated story. But it at least initially is presented to us as having 3 spatial dimensions. And when we start to do physics, we do it assuming there are 3 spatial dimensions, is what Newton does, and he uses Euclidean geometry and blah, blah, blah. It's presented to us as unfolding in time, ordered in time. Now, I don't see how, the question isn't how do I find time? The question is how did you ever lose it in the first place? Now, sometimes people lost it because they wrote down some equations, right? I mean, really, they lost it. They wrote down some equations, some second-order time equations, and they said, look, if I take t to minus t in these equations, they still hold. Okay, that's a kind of very esoteric way to lose track of time, or the direction of time, it seems to me. But I don't see any difficulty. I mean, I don't see any difficulty locating it in the sense that we all make judgments of time order all the time, and they're essential to our. So my idea is, look, the world presents us in a certain way. The right thing is you make adjustments to that initial presentation as is necessary by argument and by further observation. You have to start with the manifest image, and then you adjust it. And I just never thought there was any argument that we ought to adjust it by throwing the direction of time out, right? And if you don't throw it out, then it's all around you everywhere. Unlike centers of mass, which I really can't, I mean, for all I know, the center of mass of some, system is actually sitting right there, and there's no way I'm going to look right there and find it. But I don't see how the analogy, right, the time ordering of the world as presented to us is always with us. We can't get rid of it. The sense, as I said, so David has a puzzle. Let me just, maybe this will help. David has a kind of puzzle. We all have the following impression, that right now I can make decisions and carry them out that will have an effect and influence on what I eat tonight, and I can't do a damn thing about what I ate last night. And those 2 meals are, as it were, symmetrically ordered with respect to now, except with respect to the directionality, right? Now, from David's point of view, it's a bit of a puzzle why that should be so, right? Why this big difference? For me, look, time goes that. I mean, not so much of a puzzle if you think causation has, temporal priority orderings in it that nothing I can do now can have any causal effect on my past. And so, the presentness and ubiquitousness of directionality of time, right, is something that one ought to be much more shocked, I think, than people are when physicists come along and say, it's all just an illusion. I mean, there are these kind of, David doesn't say it this way, so I don't want to put words in his mouth. But Gödel does. I mean, there are a bunch of people who say, look, it's an illusion. Time is an illusion. Time is, they go Kantian. Time is produced by the human faculty of sensory perception, right? I mean, you should be astonished by that. I'm saying normal stuff. I'm saying, time passes. It goes a certain way. We're all getting older all the time. That's a physical fact.
I just wanted to put a little more positive spin on this puzzle. So I don't know how to characterize the manifest image, but I take it that it's part of the manifest image that space is directed. There's up and down, and presumably the story has something to do with gravity. That's pretty deeply ingrained in our language, and certainly in the character of our experience.
Yes.
It's the kind of thing that we don't have to deny.
Yes.
That space has a direction in that sense. We would want to say that it's definitely not fundamental. It would be a big mistake
Yes.
To build that into any kind of fundamental geometry or anything like that.
Yes.
It may well be that time is different, but it's not absurd to see that maybe it's something like that. Maybe it's a fairly superficial fact, even though it is fairly deeply embedded in our experience and in the way we talk, that that time has a direction. So sort of the authority of this is how it seems, or this is the natural way to think. How could you possibly forget about this? It is sort of being called into question when you look at these analogies.
Well, let me just, so of course you're absolutely right about, not only is the normal thought that up and down is a sort of fundamental directionality to space, but that up and down are, as it were, the same direction everywhere. Right? So that's where you got the idea. People say, well, gee, if the Earth is round, why don't the people at the Antipodes fall off, right? So down was always that way, and that's why the Earth had to be sitting on a elephant on a turtle, and then more, you kept having to add turtles because down was always that way, and you needed something supporting it. Okay, so sure, you could generalize off of your local conditions in a fairly natural way, but that turns out to be pretty bad. Now, that particular error about downness for, say, even Aristotle, where he made down toward the center of the universe, and so the people on the Antipodes are fine, and you don't need any turtles and elephants underneath to keep it from falling, right? Because it's all going to be attracted here. That was a good solution to that. I would say that upness and downness do not play this ubiquitous role in, say, the notion of causation, right? I mean, there are lots of cases where you can, I don't need to indicate which way was up and which way was down, as it were, to figure out what caused what. But if I tell you something, but I don't give you the time order in which they happened, you might say, I can't tell what's causing what, because you're not telling me what's first and what's later. So the sense in which the direction of time is very deeply embedded in a lot of fundamental explanatory notions, I think, is qualitatively quite different than upness and downness. Right? Wrong.
I think so. On the one hand, this is Professor Albert's, as I understand it. On the one hand, trust the physics. It's worked incredibly well for us, and if you believe in the physics, before the initial condition of the universe, there is the symmetric pattern of time going this way and events lining up that way. Right? Initial condition of the universe. We just happen to be living in a time where the initial condition is behind us and we're going in this direction.
Wait, there's a couple of presuppositions there that are worth unpacking. If something like general relativity is true, on versions of cosmology that we sometimes currently entertain, there may or may not be a time on the other side of the entropy minimum that you're talking about. So, and I'm not sure that the difference between Tim and me can easily be characterized in terms of how much we're impressed with how well physics has done so far. I think we're both pretty impressed with how well physics has done so far.
We're both impressed, but also, as David was saying, I mean, in response to Chris's question, following out his line of inquiry, right, following out his project was leading him to things that would be, quite extraordinarily new, let me say. If you said, these knotted topological structures are going to be the foundation or that it's got to be field theoretic. I mean,
Right.
that's not stuff you're finding in physics. It's stuff that
physics
would have to adapt itself to.
The reason Chris raised this
correct.
question is precisely because it's coming up in other areas of
Yeah.
physics now. But yeah, but I mean, but I'm sorry, we both cut you off before either of us understood your question.
As I understood it, you are saying that like time is, as it says in physics,
You mean if I'm buying into what say some continental philosophers refer to as the spatialization of time? Yes, I'm buying into that more than Tim is. That seems like a fair distinction. Yes.
What he's saying, if I understood you correctly, is trust that time is this way, the way you trust that this chair is here. You didn't. Prior to taking any philosophy course, you did not question that this was here, right? It's something we just saw, we take for granted that it's there.
Right.
And likewise, it's in every, part of our experience that time.
Oh, okay. This is now Tim's view. Yeah, yeah, I agree with. I think Tim agrees with that.
Can I actually just make a quick comment here? The actual practice of physics and science in general. I don't think David's going to disagree about this. When scientists set out to write a paper saying, I'm going to explain this, or, they always treat the time direction in a certain way, right? And they talk about initial conditions and later things and this causing that and so on. So it's not as if looking at scientific practice, right, there's all kinds of what look like, depending on the direction of time being there and playing a certain kind of role in producing explanations.
But there's nothing about that practice. If there's supposed to be something about that practice that indicates that they're treating that direction as fundamental.
No, I'm not saying. I'm saying no.
Okay,
I'm saying it's neutral. In that sense, it's neutral between us.
Right.
Not that it's on my side. I'm just saying it's neutral between us.
Good. I agree.
So I'm not saying, ignore what science is telling. I mean, it sounded like you were saying, David saying, listen to science and ignore it. And I'm saying,
In terms of thinking about time, I think you were saying it's fundamental, and if somebody were to ask, well, what do you mean by like something being fundamental? Then it means something approximately like intuitively you know it to be.
No, not intuitive at all. Look, the fundamentality of time structure. I mean, there's nothing intuitive about the time structure of relativity, which is what I ended up with. It's actually very unintuitive, right? No, I mean, people don't grow up thinking relativistically at all. So I'm not appealing, in that sense, what the actual structure is. I'm not saying, gee, just trust your intuitions or anything like that.
Our experience?
What I said was that the world is presented to us as, I mean, experience is not a word I like to get into. I mean, because I don't know how to explain anybody's literal experience of anything. And David made clear he really talks about experience but doesn't mean conscious experience.
Right.
I mean, we're all caught with the mind-body problem, right? What I talked about was the way the world is presented, as it were, initially presented, the way we would describe it. And that's not about my experience. It's about like saying, when I say space is three-dimensional, that on the face of it is not a claim about my experience of anything. It's a claim about space, right?
But time is a thing that's not. Time is a thing, and that it has a geometrical structure like space, but a different one.
Yeah.
One that has directions.
Yes.
So it's ontologically more crowded than.
I mean, it's different from space in that. Look, there is no. When I say everybody, people seem so amazed at this. People say, look, there's no point crying over spilled milk. That's a temporally directed comment, right? I mean, There is a point in being careful not to spill your milk, right? If you haven't spilled it yet. But there's no point in crying over it once it's done. Okay, that's just, that sort of simple thing that everybody understands has a temporal asymmetry embedded in it. It's one we're all familiar with.
There's another question back here, and then you'll be next.
I'm afraid this might kind of reveal my biases, but I wonder if you might, Professor Albert's view, starting from, say, the Hamiltonian and moving towards an account of temporal experience or taking time as non-fundamental as somehow, well, it's certainly, it's less metaphysics first, right? And it might be, you might consider it more economic. Maybe that's not the right way to characterize it, but I see the Maudlin's view as okay, let's start with fundamental physical or geometrical structure, and then let's build up and explain how experience works from there. Whereas, or how we experience time and all these features of the temporal aspects of our language and explanations. Whereas something like the converse is going on that you might be inclined to view as somehow more, maybe more economical, or you're not pleasant. There's no sort of metaphysical primitive involved in the former kind of explanation, or it doesn't seem to me that there is. You're relying on just the dynamics and characterizing how the appearance and the temporal aspects of our language follow from that, while giving some explanation, posterior explanation of these other features like asymmetry and epistemic access through these other means. I'm inclined to think that's a nice unifying view, and it doesn't require the same kind of, maybe it's slightly more Kantian or anti-realist or something, but do you see any kind of differences like that between the views?
I mean, I think David put it pretty well, but I don't think it maps onto what you just said. David thinks dynamics first, geometry derived. I think the geometry constrains the dynamics, right? So, I mean, imagine somebody says, having just learned special relativity, and they say, really, what is the fundamental postulate of special relativity? It's a postulate about the geometrical structure of space-time. It's Minkowski's structure. And then you say, now you're going to write, I haven't said a word about dynamics. Right? And now I say, now I'm going to write down some dynamics. I say, well, you're going to be really constrained, because you better be able to express your dynamics using only that structure. Whatever you write down mathematically, if that's all the structure there is, if that's all the space-time structure there is, then of course your dynamics, however you express it, better be expressed solely in terms of that structure. So that's a kind of geometry constrains dynamics. Now David wanted to say dynamics produces geometry, and what constrains his dynamics was this very, very, very weak thing. I mean, that was what this discussion was about. I don't see either of these as being more or less metaphysics-y than the other. I mean, we have different starting points, and we're seeing what happens if you try and, I mean, David arrives at a certain thing that Chris was getting into by taking the dynamics first. I tend to think of the geometry first, and the geometry constraining the dynamics, and I want to write the dynamics down in terms of fundamental geometrical structure rather than deriving the fundamental geometrical structure from the dynamics. I just don't see this being, either of us being more or less Kantian or even more or less economical, quite honestly. Exactly. I mean, maybe you think there's more to say there.
I mean, I think I agree with almost everything Tim said. The only, I guess, the way I was presenting it here, there's a step that comes before the dynamics. In order to even begin to talk about dynamics, you need a foliation into times, and then and the way you see that is you need to discover that there's a way of foliating the arena such that there are simple rules connecting the leaves. Once you've got that, you've got a dynamics, and then you're off to the rest of it. Right.
Well, I'm in an embarrassing condition of having put down the wrong time for this, so I came time after you. And I can't, I'm told maybe I can get it, online or something. But it's trying to sort out which is which. The impression I'm left with is that when it comes to saving the phenomena, as Plato says, as far as it's you're saying you can't. The phenomena being the reversibility of time. And he's saying, if you do his...
No, I don't understand that. I think we're both... I think the game for both of us is saving the phenomenon.
Oh, I don't, but I thought you said in the end you can't say why.
What
It has the apparent directionality. I mean, the appearance is the phenomenon.
Right.
David certainly wants to think he can, at the end of the day, explain why
Yeah.
there are asymmetries in the way things are distributed.
Right. Right. And why we say the stuff we do about time directionality. No, I think we're both thinking we can save that. I think like Tim has been saying, the difference is where to start and what to take as primitive.
Okay.
And in that way, I mean, the way Tim began to set up his talk was very helpful for this discussion in that kind of way.
Yes.
I have a question for Professor Albert. So when you're talking about prediction or retrodiction versus measurement, when you're predicting a set of XYZ coordinates based on your W coordinate or based on your time, right? Is that inherently just an infinite wave function, or is it constricted by a light cone? And if it is constricted by a light cone inherently, would you run into a problem there because light cones are directional?
So there's tons of that went over my head. Let me start to try to unpack it. Oh, by the way, in relation to your question, one thing Tim said a couple of times. Oh, in the relativistic case, you're not going to get the kind of foliation that David wants in the way that he wants it. I don't think that's true. In the difference between a relativistic theory and a classical theory, one of the differences is going to be you have this distribution, and you find that there are lots of ways of cutting up the space that produce these rules. There's an infinite number of ways that end up corresponding to all of the space-like foliations. That's equivalent, of course, to the light cone structure. So no, I don't think there's any. I don't think there's any sense in which relativity was producing something other than what I had in mind. Now when you talk about an infinite wave function, let's see. First of all, most of what I was talking about was just classical physics stuff. So I lost you at the infinite wave, and I'm not even sure I know what an infinite wave function means.
But if we put it into like the billiards table thing,
Yeah.
so you're saying like we can't use the measurement method, right, on the future, right, only the past?
Yeah. It's one of the things that a view like mine is going to have to aim to explain. Okay, why it is, given the symmetry of the dynamical laws, that we have this measurement or recording type of access to the past and not to the future. And the proposal was, because if you go towards the past, this regress of, well, I know this because I have a record of that, and I know that because I have a record of that, blah, 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 blah. You need all of these things that I was calling ready states that you have one handy ultimately in the past in the form of this past hypothesis that you need in order to explain thermodynamics. You don't have one towards the future, and that's supposed to be the beginning of an account of why we have this kind of record or measurement type epistemic access toward the past and not toward the future. Right.
So according to that line of thinking, there is like an uncertainty about the future, right?
Purely epistemically, yeah. In the classical case, it's purely epistemic. It's not like, uncertainty in quantum mechanics is a really bad historical accident because it makes it sound like there's an epistemic issue there, whereas depends on your way of solving the measurement problem. But on the standard presentations of quantum mechanics, on the textbook presentations of quantum mechanics, there's a metaphysical issue there, not an epistemic issue. Classically, it seems appropriate to say there are all kinds of things about the future of which we're uncertain. It's a lot harder to get an epistemic purchase on all kinds of aspects of the future than it is on all kinds of aspects of the past. And yes, the proposal is that what lies behind that asymmetry is the fact that in one temporal direction there's a past hypothesis, and in the other there isn't one. Right.
We can be certain that whatever happens in the future, if we just look at the x direction, the change in that x direction can't exceed what would happen at the speed of light, right?
In a relativistic theory, but I'm not sure why we're getting into relativity here. I mean, maybe there's a good reason. I'm not sure. If we want to start talking about relativistic theories, that's right. I don't think the distinction between relativistic theories and non-relativistic theories was playing any crucial role in what I was trying to say. I'm sorry, I did a really bad job of figuring out what the question was.
We've got two more questions in the back first, and then we'll be next. Yeah.
Okay, so this is what I'm probably. On the Professor Maudlin theory, you postulate as a fundamental the line. The directional line is the fundamental element, on which you have a certain restriction. You get a light cone restriction, etc., etc. Then you're hoping there will be some dynamic laws on top of that, and they will react into directionality, etc., etc. Now, if we're taking the Professor Albert's view with the emergent space, then the first thing the theory which would work in that line is we have to explain, it will have to instantialize some sort of theory.
It'll have to whatalize?
The word which David Wallace uses a lot.
Which word does David Wallace use a lot? What?
Like an instance on the
Instantiate?
Oh, instantiate. Okay. Does David Wallace use that word? Yeah. Okay. Yeah. It'll have to. Yes. Yes.
You have to instantiate something like in physics we have, which probably the first thing which has to be instantiated is a path, and the first thing which has to be instantiated is a directional path. So in a way, we're getting right where Professor Maudlin's theory was starting. We have a path, and it's a directional, and we go back into stating all the because also we have to, if we want to relativistic theory, we have to instantialize the light cone structure, the metric, etc. So basically, we have the whole the same theory, which Professor Maudlin was describing. Only now it's an emergent theory under Professor Albert's terms.
I mean, I'm not sure how much of this I understood, but it seems like Tim wants it to be the case that there are facts about these lines and their directednesses before you start talking about how mass and matter and fields are distributed over space-time. That's in the fundamental structure of space-time itself. And it's also, it's right that whatever whatever distinctions there are in our experience of the world had better be locatable somewhere in both of our accounts of the world. And in my account, in the kind of account that I'm trying to pursue, you're right in saying it would have to be rooted in the distribution of matter and fields and stuff like that. You seem to say something further, that's the first structure that would appear, or some. I'm not sure I knew what that meant.
We're trying to. I didn't want to use the Hebrew word, which we don't like in this concept, which is ever.
Which is what?
Ever.
Oh.
if we get rid of paths, meaning we're not talking about Gaussian mechanics, then if it's a pure wave mechanics, the only way to instantiate physics would be to somehow instantiate paths which behave according to classical laws. And that's the step we're trying to refer to. The first thing which we will have would be a path and direction.
Oh, okay. But now it sounds like you're talking about a problem that's specific to something like Everett.
Well, I didn't want to say that because it's not.
Well, but I'm not. For example, in Bohm, there isn't going to be an issue like that. It's right. The paths are right there of the particles. So I'm not. So yeah. Now it sounds like you're talking about a worry that's specific to something, to a particular way of trying to understand quantum mechanics, and a way that, as you anticipated, I think, and I think Tim thinks, there are all kinds of other reasons why it's just not going to pan out anyway.
You don't think it's going to pan out as the emergent theory?
I don't think Everett is going to pan out as a way of understanding quantum
No, not
mechanics.
Everett. I mean, that's what I want to say, because it's not any theory which is intrinsically wave mechanics, which somehow substantiates.
I don't know what intrinsically is. GRW something that's intrinsically wave mechanics? Is Bohm something that's intrinsic? I guess Bohm is supposed to be not something that's intrinsically wave mechanics.
Well,
I don't know whether GRW is something that's intrinsically wave.
With Bohm, the problem is that the path of the particle to which we don't have a epistemic axis,
right,
does it still belong to the realm of the lines which are fundamental?
No, it's those lines are in the geometry. I mean, I'm speaking for Tim here, but those lines are there before there's any talk of what it is that occupies space-time.
I mean, what maybe we should, nothing really David said or I said had anything to do with quantum. I mean, bringing quantum mechanics on top of the mess we're in.
We have enough stories.
Yeah, exactly. So that's already. But I mean, maybe this will help in terms of the difference, because David said very directly. He said, all right, he was starting with just this four-dimensional differentiable manifold, and then putting stuff on it in a certain distribution. Now, distribution's a little tricky there, because you normally think of a distribution already as giving distances and various geometrical relations between things.
Topology,
so it's a something. But because this four-dimensional manifold he's starting with makes no distinction, as it were, between space and time, as he said, if he can do it this way, and then on the very same manifold, as it were, paint another non-interacting story that way, and another one that way, and the time directions of all these different stories would be pointing in different ways, as it were, if we could compare them locally, right? On my picture, certainly in the relativistic case, the fundamental thing already has a single light cone structure built into it. It's there at the most fundamental geometrical level. So you can't just then say, oh, add another one that's going this way and add another one going this way. No, it's, so he's working, he is starting with something. It has a lot less structure built into it.
Yes. That's right.
And because it has a lot less structure built into it, there has to be a much greater story about how the structure we think we're familiar with emerges by some other means.
So there's one more question.
Yeah, so I have a question for Professor Maudlin. So you have a fundamental concept of direction of time. So and then you start with a directed linear structure from which you generate a topology. And that gives you a geometry of cosmic space.
Or any globally hyperbolic. I mean, you could tell the same story for any globally hyperbolic.
You could possibly go to a cosmic space that has
Yeah.
So I'm wondering, is there a mathematical proof that actually does from a directed linear structure to go to a cosmic space?
I mean, yeah. Again, it's not really. I mean, there are lots of proofs that have been around forever in just standard GR, general relativity. What gets built in on my way of doing things is what would be called the conformal structure, which is just the light cone structure. So it's weaker than Minkowski space-time. Okay? And there are lots of proofs that go back forever that basically say the conformal structure follows from what's called the causal structure, but the causal structure is nothing but a partial ordering among events by earlier and later. That's what the causal structure is. I mean, it really doesn't have to do with causation. It's a funny word for it. It's really temporal. It is the order of the temporal ordering structure that's implicit in a general relativistic space-time. So yeah, there are lots of. I mean, those theorems have been around forever. They're not due to me, and I can just wave at them basically. and say, see?
What would be a good keyword to search for this?
Goes back to Hermann Weyl, it's the first one, and then there were a bunch of proofs in the 70s about characterizing the conformal structure plus topology or metric structure on the time-wide geodesics.
Yeah. Yeah, Chris actually knows the history of that better than I do, but we can.
Well, I think if there aren't any further questions, I want to thank our speakers for exemplifying a fruitful yet challenging discussion on a very difficult topic. So thanks a lot.
Thank you. That was great. Thanks.